Welcome to the ENME 351 video lecture series. This is part one of a three-part installment on improved filters. In this lesson, we'll focus on higher order filters. Recall that a first order filter that was defined in part by its magnitude ratio. For example, for a low pass filter, we had a magnitude ratio that looks similar to this. Here we have 1 over the square root of 1 plus omega over omega c. And recall that omega c, that's the corner or cutoff frequency for our filter. For higher order filters, what we'll add here is a 2 times k to this omega over omega c term. K in this case is going to be the order of the filter. We also define a phase shift where the phase shift is going to be equal to the summation of a bunch of first order phase shifts, and we'll sum from I equals 1 to k. As an example then, let's take a look at a second order system. So k will be equal to 2. We'll take a look at the magnitude of an input frequency that is equal to 10 times the corner frequency. So our input frequency omega is going to be equal to 10 times omega c. So this will be equal to 1 divided by the square root of 1 plus omega divided by omega c, that'll be 10 omega c divided by omega c, or 10, all raised to the 2 times k power. So it'll be 2 times 2, or 10 to the 4th power. So this is effectively 1 over 100, or 0.01. As another example, let's look at a fourth order filter, so k is equal to 4, and let's look at the magnitude ratio at the same input frequency, so 10 times the cutoff frequency. That results in a 1 over the square root of 1 plus the quantity 10, all raised to the 2 times 4 power, so 10 to the 8th power, which results in a 0.0001 magnitude ratio. So what we see here then is by increasing the order of the filter, we're creating a much steeper transition from our pass band to our stop band occurring at the cutoff frequency. So let's take a look at this graphically. Here I've rewritten my magnitude ratio, where the magnitude ratio is equal to 1 over the square root of 1 plus the quantity omega over omega c, all raised to the 2k power, where k is the order of the filter. And at left, I'll be plotting the response of filters for different orders. Let's start with a first order filter. For low input frequencies, I'm at 0 dBs. At my cutoff frequency, omega c, I drop down to minus 3 dBs. At 10 times the cutoff frequency, I've dropped down to minus 20 dB. At 100 times the cutoff frequency, I've dropped down to minus 40 dB. And at 1,000 times my cutoff frequency, I've dropped down to minus 60 dB. So if I stitch these together then, I get the response of my first order filter. Let's move up now to a second order filter. I'm at 0 dB for low input frequencies. At my cutoff frequency, I'm once again at minus 3 dBs. At 10 times my cutoff frequency, I'm now at minus 40 dBs. So at 100 times the cutoff frequency, I'm at minus 80 dBs, and at 1,000 times the cutoff frequency, I'm at minus 120 dBs. So again, if I stitch these together, I end up with the response of my second order filter. Let's take a look at the third order filter. Same thing for low input frequencies, and at the cutoff frequency, I'm once again at minus 3 dBs. But you'll notice now in my magnitude ratio response, I'm at a power of 6. I have 2 times 3, which gives me a power of 6. So at 10 times my input frequency, I'm going to have a magnitude ratio that has been decreased down to minus 60 dBs. And then at 100 times the cutoff frequency, I'll be down to minus 120 dBs. So if I stitch this together, I'll end up with the response for my third order filter. We could continue with a fourth order. We'll be at minus 3 dBs. At 10 times the cutoff frequency, we'll be at minus 80. We stitch those together, we get the fourth order. And we could do the same thing for the fifth order, or really as high of an order of filter as we'd like to go. So the takeaway here is that as the order of the filter increases, we're steepening that transition from our cutoff frequency down to higher input frequencies. So if we go from a first order down to a fifth order, we've significantly steepened that transition. So if I were to increase the order of my filter and continue to increase that, I would start to approach the performance of my ideal filter, where that transition from my cutoff frequency was a vertical line. Because our filters are not ideal, even at higher orders, we need to define this term attenuation. The attenuation of a filter is the amount by which unwanted signals in our stop band are decreased, and this is given in decibels. We could write this for, say, a low-pass filter, where the attenuation is equal to 10 times the log base 10 of the denominator of our magnitude ratio. So that'll be 1 plus quantity omega over omega c, all raised to the 2k power. As an example, consider a second-order filter, so k will be equal to 2, and let's consider an input frequency equal to 100 times our cutoff frequency. If I plug in, I'll find my attenuation is equal to 10 log base 10 of 1 plus 100 to the 4th power. So this will be effectively 10 to the 8. So log base 10 of 10 to the 8 will be 8 times 10 will be 80 dB. So this tells me then for a second order filter at 100 times the cutoff frequency, I have 80 dBs of attenuation. We've solved this numerically, and we could also read this information off of our plot from the preceding slide. So at an input frequency of 100 times my cutoff frequency, if I go down to my second order response, I see that I have that minus 80 dBs here. So I have 80 dBs of attenuation for my second order filter at 100 times the cutoff frequency. If I were to go to higher order filters, say the fourth order filter, at that input frequency of 100 times the cutoff frequency, I'd be down around minus 160 dBs. So I'd have 160 dBs of attenuation. So we can solve this graphically or analytically, but the takeaway is that for higher order filters, I have more attenuation for the same input frequency. Let's work through an example working with a higher order filter, in this case for an audio speaker system. In this case, we're attempting to improve the performance of the speaker system by filtering out any higher frequency noise entering my subwoofer. The engineers at Bose have provided the following specifications. They're requiring a magnitude ratio greater than 0.95 at 50 hertz, at an input frequency of 50 hertz. And they need that magnitude ratio less than 0.01 by 200 hertz. So there's going to be a corner frequency or a cutoff frequency at 100 hertz. And the question then is, well, what's the order of the filter required to achieve this performance? Let's begin by writing down some of these requirements. So we have a requirement for a magnitude ratio and an input frequency of 50 hertz to be greater than 0.95. Graphically, for an input frequency of 50 hertz, I have a requirement for a magnitude ratio of 0.95. Our second constraint was a magnitude ratio of less than 0.01 at an input frequency of 200 hertz. So again, graphically, for an input frequency of 200 hertz, we have a magnitude ratio here of 0.01. So these 2 points, they're defining my transition, and the steepness of this transition, that'll define the order of the filter that's required to achieve this performance. It's also worthwhile to list our corner or cutoff frequency here, and that's at 100 hertz. Let's go back to this 50 hertz requirement for a magnitude ratio at 50 hertz. We have a magnitude ratio greater than 0.95. So at 50 hertz, the ratio of f over fc, that'll be 50 over 100, is equal to 0.5. The magnitude ratio in terms of frequency f is going to be equal to 1 over the square root of 1 plus quantity f over fc to the 2k, where k is the order of my filter, and thus k is what I'm ultimately trying to solve for in this problem. As such, let's rearrange this equation to solve for k. So k will be equal to log base 10 of 1 minus the magnitude ratio squared divided by the magnitude ratio, so 1 minus m squared over m, all divided by 2 times log base 10 of the quantity f over fc, the input frequency over the cutoff frequency. So I can plug in then and describe the order of the filter. So k must be greater than the log of 1 minus 0.95 squared divided by 0.95, all over 2 times the log of 0.5. So this requirement then for the magnitude ratio greater than 0.95 at 50 hertz is telling me that I need a filter of greater than 1.6 in terms of the order of the filter. So based on this requirement, it's telling me k must be greater than 1.6. Now, of course, we need whole numbers here. So this is telling me that I need at least a second order filter. Higher order filters will suffice for this particular requirement, but a minimum, I need a second order filter. Now let's do the same thing for the second constraint. So the magnitude ratio at an input of 200 hertz must be less than 0.01. I'll have the same equation. So k for this requirement, k must be greater than the log of 1 minus 0.1 squared divided by 0.01, all divided by 2 times the log of 2. So what this tells me is that k must be greater than 6.6. So based on this second constraint, second requirement for the problem as posed by the engineers, I'm requiring a k greater than 6.6 order filter. And once again, I must have a whole number here. So what this problem is telling me is that I'm going to need a 7th order filter to meet the performance requirements of this speaker system.